Assalamu alaikum beautiful people, welcome to the class of chemistry. This is your Harbana and I'm gonna make you learn the lesson in the most easiest possible way. If you like the video, please subscribe to my YouTube channel and do not forget to press the bell icon. So let's begin. So first of all, let me give you a brief overview about dynamic equilibrium from the previous lectures. You can check the videos from the playlist. The first characteristic of dynamic equilibrium that it can only be achieved in closed system. There are actually three types of systems. The first one is open, second one is closed, and the third one is isolated. In open system, both matter and energy can get out of the system, whereas in closed system, only energy could be able to get out of the system. And in isolated system, neither energy nor matter could be able to get out of the system. Furthermore, at equilibrium state, a reaction does not stop. It means that forward and reverse reactions keep on taking place at the same rate but in opposite direction. Another important point that equilibrium is always attained before the completion of the reaction. Here in this graph, you could clearly see that how forward reaction and reverse reaction are taking place and a time reach when both the rates become equal and they are represented by a single line. At equilibrium state, the amount or the concentration of reactants and products do not change. Even the physical properties like color, density, they also remains the same. Equilibrium is attainable from either way. It can be start from the reactants or from the products. The attainment of equilibrium vary from reaction to reaction. Equilibrium can be disturbed or can be regained under different conditions like pressure and temperature. Change in the concentration of reactants and products can also help us in disturbing or regaining dynamic equilibrium in any chemical reaction. Now let's move towards the very important topic of this book, which is known as law of mass action. This law was presented by Goldberg and Weige in 1869. Goldberg and Weige are brother-in-laws of each other. According to law of mass action, the rate at which a substance reacts is directly proportional to its active mass, and the rate of a reaction is directly proportional to the product of the active masses of reacting substances. Well, I know that you couldn't be able to understand this law in the very first time, but do not worry, I'll try my level best to make it easy for you. So if you study the first line, the rate at which a substance reacts is directly proportional to its active mass. It means that the speed of the reacting substance is directly proportional to the concentration of a substance. Or you can say active mass. Now we will see that what does active mass means. Active mass is the molar concentration, that is the number of moles per liter, and we all know that mole is the amount of mass of a substance containing Avogadro's number, which is 6.02 into 10 raised to power 23. Apologies for some misprinting here. Well, active mass is expressed by enclosing the formula in square brackets and its unit is mole per dm cube. Additionally, this law states that the speed of the overall chemical reaction is directly proportional to the product of the active masses of the reactants. Now let's explain this law with the help of a general reaction in which A and B reactants react together to give C and D products, and this reaction is reversible reaction, which means that products can be converted back into the reactants. Suppose A, B, C and D in the brackets are the molar concentration of A, B, C and D respectively. According to the law of mass action, the rate of forward reaction is directly proportional to the active masses of reactants, whereas in case of reverse reaction, the rate is directly proportional to the product of the active masses of the products. So in the case of above general equation, the rate of forward reaction is directly proportional to the product of the active masses of the reactants. Removing the sign of proportionality, there should be a proportionality constant, and for forward reaction it is Kf. The reverse reaction will be represented in the same way. and the proportionality constant here is Kr. Dear students, Kf and Kr are the specific rate constant for forward and reversible reactions respectively. At equilibrium state, the rate of forward reaction is equals to the rate of reverse reaction. Now, by putting the values of forward reaction and reverse reaction, we got Kf concentration of A into concentration of B is equals to Kr concentration of C into the concentration of D. On rearranging the above equation, we will get Kf by Kr, which is equals to the concentration of product by the concentration of reactants, where Kf by Kr is equals to Kc, and this Kc is known as equilibrium constant. Now we will see the derivation of the expression for equilibrium constant for another general equation. This general equation is similar to the previous one, but here the number of moles for reactants and products are given. This reaction is also reversible. It means products can be converted back into the reactant. In this reaction, small a, b, c, and d are the number of moles for capital A, B, C, and D. And it is clearly shown here that A and B are the reactants, whereas C and D are the products. So for these type of reactions, the law of mass action states that the rate of a chemical reaction is directly proportional to the product of a molar concentration of its reactant raised to the power equal to their number of the moles in the balanced chemical equation of the reaction. No need to worry again. It is just simply saying that the number of moles will be raised to the power on the molar concentration of reactants and products. Let us first discuss the forward reaction. A and B are the reactants, whereas small a and small b are their number of moles. The rate of forward reaction according to the law of mass action is Rf is directly proportional to molar concentration of A power small a and molar concentration of B power small b. Removing the proportionality constant, Rf is equals to Kf molar concentration of capital A power small a product molar concentration of B power small b, and these small a and b are the number of moles of these reactants. Kf is the rate constant for forward reaction. Similarly, the rate of reverse reaction R, small r, is directly proportional to the product of concentration of C power small c, concentration of D power small d, where small c and small d are the number of moles as given in the balanced chemical equation. So again here, the relationship can be written as RR is directly proportional to the product of the products having number of moles in their power. Removing the proportionality constant, RR is equals to KR multiplied by molar concentration of C and D having their number of moles in their powers, where Kr is the rate constant for reverse reactions. Now, the above derivation would be same as we have studied before, that at equilibrium the rate of forward reaction is equals to the rate of reverse reaction, such as Rf is equals to Rr, and by putting their values we get Kf molar concentration of A and B having number of moles in the power is equals to Kr multiplied by molar concentration of C and D having their number of moles in their powers. On rearranging the above equation, we take the constant variables on one side and the reactants and products on the other side. We will get Kf by Kr is equals to product of products divided by product of reactants. And we have studied previously that Kf is equals to Kr is equals to Kc, which is known as equilibrium constant. In other words, we can say that equilibrium constant is the ratio of the product of products to the product of the reactants taking place in a balanced chemical equation. This type of derivation is not much different from the previous one. There is just the addition of number of moles, which are raised to the powers of their respective species. This is one of the easiest law of chemistry and mine favorite as well. Now we will explain this law with the help of some examples. The first example explained in your book is the production of nitrogen monoxide. When nitrogen reacts with oxygen, nitrogen monoxide takes place and it is a reversible reaction. So according to the law of mass action, the rate of forward and reverse reaction are written here, and the equilibrium constant, which is Kc, is equals to product divided by the reactant. The product is nitrogen monoxide, which has 2 number of moles, and it comes to the power, whereas reactants are nitrogen and oxygen. These are 1 moles each, and unity is usually not written in the power. The next example is the production of ammonia, which is formed from 1 mole of nitrogen and 3 moles of hydrogen. The rate of forward and reverse reaction for this chemical reaction are written in the same way, and the Kc is expressed as ammonia power 2 divided by nitrogen and hydrogen powers 3. Now I will explain you more about equilibrium constant and its units. We know that equilibrium constant is represented by Kc, which is the ratio of product of concentration of products raised to the power of coefficient to the product of concentration of reactants raised to the power of coefficients. This is the same formula, but it is just explained in words here. We conventionally write the products as numerator and reactants as denominator. There is no proper reason for writing products and reactants this way while writing a chemical equilibrium constant. To write an equilibrium constant, balanced chemical equation is a mandatory condition. Until the chemical equation is not balanced, you could not be able to write or give the correct expression for chemical equilibrium for that particular chemical reaction. The value of Kc depends on temperature. It does not depend on its initial concentration of reactants and products. Kc has no units in the reaction with equal number of moles on both the sides of the equation. This is because the concentration units cancel out in the expression for Kc. Let us take an example for this case where hydrogen iodide is formed from the reaction of hydrogen and iodine. In this chemical reaction, the number of moles are equal in both the sides. 1 mole of hydrogen and 1 mole of iodine sums up together to form 2 moles of reactants, whereas in products it's already 2 moles of hydrogen iodide. If we write the Kc for this type of reaction and if we write the units, they ultimately cancel out each other, and Kc got no units for these type of reactions. Let us take another example where the number of moles are not equal on both the sides. In this example, 1 mole of nitrogen and 3 moles of hydrogen combine together to give 2 moles of ammonia. If we write Kc for this type of chemical reaction, you can see after putting the units, we finally got 1 by mole per dm cube whole square. And it finally comes up as mole raised to power minus 2 and dm raised to power 6. If you have any question relating to this lecture, you can ask in the comment box. Thank you so much.